Principal component analysis is a statistical procedure that uses an orthogonal transformation to convert a set of observations of possibly correlated variables into a set of values of linearly uncorrelated variables called principal components. The number of principal components is less than or equal to the number of original variables. This transformation is defined in such a way that the first principal component has the largest possible variance, and each succeeding component in turn has the highest variance possible under the constraint that it is orthogonal to the preceding components. The resulting vectors are an uncorrelated orthogonal basis set. The principal components are orthogonal because they are the eigenvectors of the covariance matrix, which is symmetric. PCA is sensitive to the relative scaling of the original variables. PCA was invented in 1901 by Carl Pearson. As an analog of the principal axis theorem in mechanics, it was later independently developed by Harold Hotelling in the 1930s. Depending on the field of application, it is also named the discrete Kosambi-Kahn-Lover transform in signal processing, the Hotelling transform in multivariate quality control, proper orthogonal decomposition in mechanical engineering, singular value decomposition of X, eigenvalue decomposition of XTX in linear algebra, factor analysis, Eckert-Young theorem, or Schmidt-Mirsky theorem in psychometrics, empirical orthogonal functions in meteorological science, empirical eigenfunction decomposition, empirical component analysis, quasi-harmonic modes, spectral decomposition in noise and vibration, and empirical modal analysis in structural dynamics. PCA is mostly used as a tool in exploratory data analysis and for making predictive models. PCA can be done by eigenvalue decomposition of a data covariance matrix or singular value decomposition of a data matrix, usually after mean centering the data matrix for each attribute. The results of a PCA are usually discussed in terms of component scores, sometimes called factor scores, and loadings. PCA is the simplest of the true eigenvector-based multivariate analyses. Often, its operation can be thought of as revealing the internal structure of the data in a way that best explains the variance in the data. If a multivariate dataset is visualized as a set of coordinates in a high-dimensional data space, PCA can supply the user with a lower-dimensional picture, a projection or shadow, of this object when viewed from its most informative viewpoint. This is done by using only the first few principal components so that the dimensionality of the transformed data is reduced. PCA is closely related to factor analysis. Factor analysis typically incorporates more domain-specific assumptions about the underlying structure and solves eigenvectors of a slightly different matrix. PCA is also related to canonical correlation analysis. CCA defines coordinate systems that optimally describe the cross-covariance between two datasets, while PCA defines a new orthogonal coordinates system that optimally describes variance in a single dataset. Intuition. PCA can be thought of as fitting an n-dimensional ellipsoid to the data, where each axis of the ellipsoid represents a principal component. If some axis of the ellipse is small, then the variance along that axis is also small, and by omitting that axis and its corresponding principal component from our representation of the dataset, we lose only a commensurately small amount of information. To find the axis of the ellipse, we must first subtract the mean of each variable from the dataset to center the data around the origin. Then, we compute the covariance matrix of the data, and calculate the eigenvalues and corresponding eigenvectors of this covariance matrix. Then, we must orthogonalize the set of eigenvectors, and normalize each to become unit vectors. Once this is done, each of the mutually orthogonal unit eigenvectors can be interpreted as an axis of the ellipsoid fitted to the data. The proportion of the variance that each eigenvector represents can be calculated by dividing the eigenvalue corresponding to that eigenvector by the sum of all eigenvalues. It is important to note that this procedure is sensitive to the scaling of the data, and that there is no consensus as to how to best scale the data to obtain optimal results. Details. PCA is mathematically defined as an orthogonal linear transformation that transforms the data to a new coordinate system such that the greatest variance by some projection of the data comes to lie on the first coordinate, the second greatest variance on the second coordinate, and so on. Consider a data matrix, X, with column-wise zero empirical mean, where each of the n rows represents a different repetition of the experiment, and each of the p columns gives a particular kind of feature. Mathematically, the transformation is defined by a set of p-dimensional vectors of weights or loadings that map each row vector of X to a new vector of principal component scores, given by in such a way that the individual variables of T considered over the dataset successively inherit the maximum possible variance from X, with each loading vector W constrained to be a unit vector. First component. The first loading vector W thus has to satisfy equivalently. Writing this in matrix form gives, since W has been defined to be a unit vector, it equivalently also satisfies the quantity to be maximized can be recognized as a Rayleigh quotient. A standard result for a symmetric matrix such as XTX is that the quotient's maximum possible value is the largest eigenvalue of the matrix, which occurs when W is the corresponding eigenvector. With W found, the first component of a data vector X can then be given as a score T1 equals XW in the transformed coordinates, or as the corresponding vector in the original variables, XW, W. Further components. The KTH component can be found by subtracting the first k-1 principal components from X, and then finding the loading vector which extracts the maximum variance from this new data matrix. It turns out that this gives the remaining eigenvectors of XTX, with the maximum values for the quantity in brackets given by their corresponding eigenvalues. Thus, the loading vectors are eigenvectors of XTX. The KTH component of a data vector X can therefore be given as a score Tk equals XW in the transformed coordinates, or as the corresponding vector in the space of the original variables, XW, W, where W is the KTH eigenvector of XTX. The full principal component's decomposition of X can therefore be given as where W is a P by P matrix whose columns are the eigenvectors of XTX. Covariances. XTX itself can be recognized as proportional to the empirical sample covariance matrix of the dataset X. The sample covariance Q between two of the different principal components over the dataset is given by where the eigenvalue property of W has been used to move from line 2 to line 3. However, eigenvectors W and W corresponding to eigenvalues of a symmetric matrix are orthogonal, or can be orthogonalized. The product in the final line is therefore 0. There is no sample covariance between different principal components over the dataset. Another way to characterize the principal components transformation is therefore as the transformation to coordinates which diagonalize the empirical sample covariance matrix. In matrix form, the empirical covariance matrix for the original variables can be written. The empirical covariance matrix between the principal components becomes where lambda is the diagonal matrix of eigenvalues lambda of XTX being equal to the sum of the squares over the dataset associated with each component K. Lambda equals sigma I Tk2 equals sigma I W2. Dimensionality reduction. The faithful transformation T equals XW maps a data vector X from an original space of P variables to a new space of P variables which are uncorrelated over the dataset. However, not all the principal components need to be kept. Keeping only the first L principal components, produced by using only the first L loading vectors, gives the truncated transformation where the matrix TL now has n rows but only L columns. In other words, PCA learns a linear transformation where the columns of P times L matrix W form an orthogonal basis for the L features that are decorrelated by construction of all the transformed data matrices with only L columns. This score matrix maximizes the variance in the original data that has been preserved while minimizing the total squared reconstruction error or. Such dimensionality reduction can be a very useful step for visualizing and processing high-dimensional datasets, while still retaining as much of the variance in the dataset as possible. For example, selecting L equals 2 and keeping only the first two principal components finds the two-dimensional plane through the high-dimensional dataset in which the data is most spread out. So if the data contains clusters, these two may be most spread out, and therefore most visible to be plotted out in a two-dimensional diagram, whereas if two directions through the data are chosen at random, the clusters may be much less spread apart from each other, and may in fact be much more likely to substantially overlay each other, making them indistinguishable. Similarly, in regression analysis, the larger the number of explanatory variables allowed, the greater is the chance of overfitting the model, producing conclusions that fail to generalize to other datasets. One approach, especially when there are strong correlations between different possible explanatory variables, is to reduce them to a few principal components and then run the regression against them, a method called principal component regression. Dimensionality reduction may also be appropriate when the variables in a dataset are noisy. If each column of the dataset contains independent identically distributed Gaussian noise, then the columns of T will also contain similarly identically distributed Gaussian noise. However, with more of the total variance concentrated in the first few principal components compared to the same noise variance, the proportionate effect of the noise is less. The first few components achieve a higher signal-to-noise ratio. PCA thus can have the effect of concentrating much of the signal into the first few principal components, which can usefully be captured by dimensionality reduction, while the later, principal components may be dominated by noise, and so disposed of without great loss. Singular value decomposition. The principal components transformation can also be associated with another matrix factorization, the singular value decomposition of X. Here sigma is a n by p rectangular diagonal matrix of positive numbers sigma, called the singular values of X. U is an n by n matrix, the columns of which are orthogonal unit vectors of length n called the left singular vectors of X, and W is a p by p whose columns are orthogonal unit vectors of length p and called the right singular vectors of X. In terms of this factorization, the matrix XTX can be written comparison with the eigenvector factorization of XTX establishes that the right singular vectors W of X are equivalent to the eigenvectors of XTX, while the singular values sigma of X are equal to the square roots of the eigenvalues lambda of XTX. Using the singular value decomposition, the score matrix T can be written and so each column of T is given by one of the left singular vectors of X, multiplied by the corresponding singular value. This form is also the polar decomposition of T. Efficient algorithms exist to calculate the SVD of X without having to form the matrix XTX. So computing the SVD is now the standard way to calculate a principal components analysis from a data matrix, unless only a handful of components are required. As with the eigen decomposition, a truncated n times L score matrix TL can be obtained by considering only the first L largest singular values and their singular vectors. The truncation of a matrix M or T using a truncated singular value decomposition in this way produces a truncated matrix that is the nearest possible matrix of rank L to the original matrix, in the sense of the difference between the two having the smallest possible Frobenius norm, a result known as the Eckert-Young theorem, 1936. Further considerations. given a set of points in Euclidean space. The first principal component corresponds to a line that passes through the multidimensional mean and minimizes the sum of squares of the distances of the points from the line. The second principal component corresponds to the same concept after all correlation with the first principal component has been subtracted from the points. The singular values are the square roots of the eigenvalues of the matrix XTX. Each eigenvalue is proportional to the portion of the variance that is correlated with each eigenvector. The sum of all the eigenvalues is equal to the sum of the squared distances of the points from their multidimensional mean. PCA essentially rotates the set of points around their mean in order to align with the principal components. This moves as much of the variance as possible into the first few dimensions. The values in the remaining dimensions, therefore, tend to be small and may be dropped with minimal loss of information. PCA is often used in this manner for dimensionality reduction. PCA has the distinction of being the optimal orthogonal transformation for keeping the subspace that has largest variance. This advantage, however, comes at the price of greater computational requirements if compared, for example and when applicable, to the discrete cosine transform, and in particular to the DCT2, which is simply known as the DCT. Nonlinear dimensionality reduction techniques tend to be more computationally demanding than PCA. PCA is sensitive to the scaling of the variables. If we have just two variables and they have the same sample variance and are positively correlated, then the PCA will entail a rotation by 45 degrees and the loadings for the two variables with respect to the principal component will be equal. But if we multiply all values of the first variable by 100, then the first principal component will be almost the same as that variable, with a small contribution from the other variable, whereas the second component will be almost aligned with the second original variable. This means that whenever the different variables have different units, PCA is a somewhat arbitrary method of analysis. Note that Pearson's original paper was entitled, On Lines and Planes of Closest Fit to Systems of Points in Space. In space implies physical, Euclidean space where such concerns do not arise. One way of making the PCA less arbitrary is to use variables scaled so as to have unit variance. By standardizing the data and hence use the autocorrelation matrix instead of the autocovariance matrix as a basis for PCA. However, this compresses the fluctuations in all dimensions of the signal space to unit variance. Mean subtraction is necessary for performing PCA to ensure that the first principal component describes the direction of maximum variance. If mean subtraction is not performed, the first principal component might instead correspond more or less to the mean of the data. A mean of 0 is needed for finding a basis that minimizes the mean square error of the approximation of the data. Mean centering is unnecessary if performing a principal components analysis on a correlation matrix, as the data are already centered after calculating correlations. Correlations are derived from the cross product of two standard scores or statistical moments. Also see the article by Cromrie and Foster-Johnson on mean centering in moderated regression. Much ado about nothing. PCA is equivalent to empirical orthogonal functions, a name which is used in meteorology. An autoencoder neural network with a linear hidden layer is similar to PCA. Upon convergence, the weight vectors of the K neurons in the hidden layer will form a basis for the space spanned by the first K principal components. Unlike PCA, this technique will not necessarily produce orthogonal vectors. PCA is a popular primary technique in pattern recognition. It is not, however, optimized for class separability. An alternative is the linear discriminant analysis, which does take this into account. Table of symbols and abbreviations.